I don't have the beautiful slides that Tony has. I'm sorry. But that just brought back all these memories. So it just reminds me of you know, when I was at Toronto when Tony was first there. We're just trying to figure out the timeline here. So I went there in like 83. And I was there for a couple of years as a postdoc and then converted to a professor thing. But then this new institute opened up in Berkeley, ICSI, and I went there. So I had the pleasure of, you know, working with Steve Cook and Charlie Rakoff and Joachim and all those guys and Al Borden, and it was a fantastic experience, right? And I learned a huge amount. And then I came to Berkeley and there was this new International Computer Science Institute there. And I was there as part of the theory group with Dick Karp and Lenore Blum and Manuel, I think, was even there, at least visiting or whatever. And it was a fantastic environment. It was like the golden ages of theory there. And Russell was there as a theory student. And he looked pretty much the same, except his hair was a different color. But he was just this amazing guy, you know, he was obviously brilliant and walking around. And at some point he came down to ICSI and he was explaining this new proof he had of how to convert a one-way function into a pseudo-random generator. And it was just an amazing exposition of what was going on there. And I listened to it and I said, oh, okay. And being me, who was like a debugger, I found some problems with it. And so then we figured out a way to fix those problems. And then we had this beautiful paper together. So I always feel like I'm not really a complexity theory person, but I kind of keep track of some people a little bit. So some of this stuff is way over my head, which it's fine. But that was a fantastic experience. And Leonid had kind of his own proof of it, essentially, right?
He had a bunch of, you know, I remember it. I had a kind of like jumble of ideas that I was hoping to assemble.
And they were great.
And Leonid had his own packet of ideas.
Yes.
And then you made the pieces come together.
Okay. Well, it came together wonderfully. And then then Hosted joined the group. Yeah. And he had a beautiful kind of sort of higher level proof of the whole thing that made it much cleaner and slicker, right? And so that's how Hill came to be. We always called it Hill, Hill. Or Hosted, Impagliazzo, Levin, and Luby. So that was a fantastic experience. And I've kept track of Russell over the years, and we kind of talked to each other, but never really worked that much together since then. So I'm someone with a little bit of ADD. I go off and do different things all the time. So what I'm going to talk about today is wrestling with information theory and information theoretic or bound on data integrity, longevity. And this is kind of a work that it's you know, it's after my kind of theory days. It was when I was actually at Qualcomm that I started this work. And I worked on it for a while there. And actually the first part of it was actually doing the practical part of designing real systems for distributed storage. And then there was this Simons Institute thing, which I was part of an information theory thing, coding thing. And that was really interesting. And then I was invited to San Diego to give a Shannon lecture. And I started thinking, oh, you know what? Maybe there's kind of a Shannon kind of lower bound that you can provide on some of these things. So that was really the inspiration for the work that I'm going to be speaking about here. It's really, so it kind of all comes back together to San Diego. And actually, Russell wasn't here. He was always visiting the Institute for Advanced Study back then. So anyway, I really have enjoyed knowing Russell for many years, but I'm kind of feeling, well, anyway, let me get into the talk. So wrestling with information theory. So this is kind of what inspired it. There's all these cloud storage systems out there, and this is an old picture, so they're much even bigger these days, where they have these storage clusters containing thousands and tens of thousands and hundreds of thousands of storage nodes, each with huge capacity, like 500 terabyte capacities per node. And these days, you know, it used to be back when I was a graduate student, it was based on, what was it called? I'll remember it in a minute, but it was kind of a self-contained system where you would have 3 or 4 disks and you do some kind of parity across those, right? RAID, yeah, RAID, exactly. Sorry. What's that? Came after. Yeah. So it was like, what's his name? Patterson. Yeah, exactly. Right. So that was the state of the art, but that obviously has changed at this point, just didn't scale up. So, right. So now what they do is they build these clusters on commodity hardware, and the repair and all that stuff is at a much higher level, as a software level. Right. And so at the beginning, and this was several years ago, how did they, excuse me? Just intuitively, they wanted to build it cheaply, right? So they didn't want specialized hardware. They were trying to keep the cost down as much as possible, which means it's not very robust, right? It can fail, and it does fail. In fact, this picture here shows how often it does fail, right? This was a system at Facebook, just how many failed nodes there were per day over a month, where there was a 3,000 node cluster. And these things are just failing all over the place, right? And so that's kind of why it's important that it's commodity, in the sense that it's not like a RAID system where it's designed to last. So on average, these systems will fail every 3 or 4 years. The nodes permanently fail, and transient fails are like 10 times higher than that. So in the early days, when they started going towards this, how would they get durability? They just do it by replication, typically 3 copies. Obviously, there's a lot of overhead involved in that. You have 3 times as much storage capacity as minimal you would need. And so over the years, erasure codes have become very popular to be used there, right? And all kinds of different erasure codes, Reed-Solomon codes, and other kinds of codes have been developed over the years. And so what I'm going to talk about today is a distributed storage model, where it's a mathematical model of these distributed storage systems that are based on an understanding of these deployed systems, and give a data storage capacity definition, where the goal is to reliably store these data for long durations, right? And then really focus on the lower bound part, or the data storage capacity. So just start with something that very simple, a version of what Shannon introduces is completely simplified. But the basic idea is you have a source, you want to transmit a message, there's a transmitter that converts that into a signal that's sent over a noisy channel. You have a received signal, and then the receiver converts that back into the original message. And what you'd like to have, of course, is that what you transmit is what you recover at the receiver. So in the very, very simple case, binary erasure channel, you have a transmit rate T, an erasure rate psi, and a good put rate G, which is what you're trying to maximize. And there's this very simple formula in that case, which says G is essentially 1 minus the erasure rate divided by the transmission rate times the transmission rate. Right. So let's use that same kind of thing to get a mathematical model of distributed storage. So here you have a source, you have some data X that you want to store in your storage system. You have a writer that initially stores that into the system. And the interesting part is that a lot of time passes, like a lot of time can pass between when you write it in there and when you actually access it later at a later point in time. Right. And then when you do access it, you want to read some stuff out of storage and convert that back into recovered data Z. And what obviously you want is that Z equals X, right? But the point is that there's going to be failures that are going on during that long duration of time. So this is kind of the model of how that works is you have these storage nodes and there's some large number, capital N, of those storage nodes out there. And then you have a repair that is reading data from the storage nodes, sometimes continuously, often continuously, doing some processing on that and writing it back to the storage nodes. And the reason it's doing that is because these storage nodes can fail and you lose all the data, right? Yes.
So we're talking about like erasure failures rather than
So we are at this
corruption.
point, yes, yeah. And I will talk a little bit about other errors, which are really nasty, by the way. Just the silent corruption is also a real issue. So all these systems have to do scrubbing all the time because they don't even know when they fail. But at a high level, what I'm focusing on today is the erasures. And when a node is erased, when it fails, you know it fails, right? So you kind of have an indication. The repairer knows which nodes fail. And when it fails, all the data is lost. And then you replace it with a new empty node of the same capacity, right? So we're just kind of simplifying this. Yes, Tony. That's okay. All kinds of different reasons, software failures, hardware failures. Just things happen where, you know, your computer probably, so they only fail like every 3 or 4 years. These things are operating all the time, right? So it's, you know, yeah. Yeah. But they do fail, unfortunately, and at a high enough rate that they actually have to worry about it pretty significantly. So here are the basic definitions. The raw storage capacity is just the number of nodes times the number of bits you have stored per node. So it's just n times s. There's an erasure rate, and for this conversation, we're going to assume that each individual node, eventually we're going to assume that each individual node fails at some Poisson rate lambda. So the overall erasure rate is just lambda times the capacity. And then there's going to be some read rate at which the repairer reads data from the nodes. And that can be variable, but you know, you can kind of average it out and kind of get some average rate. And then there's the data storage capacity, which is actually how much data can you actually store in this system? And that's what capital D is. Obviously, it's most C, but it can be less than C. And so here's the kind of the fundamental formula in this model, which is that the data capacity is equal to 1 minus the erasure rate times twice the repair rate times the total capacity. That make sense? Yeah, it's a great question, and it'll come up. But it's kind of fundamentally there. And that's kind of one of the interesting things about it. So just rewriting that in a different way, there's this main lower bound result, and essentially it says as things scale up to infinity, as the number of nodes scales to infinity and the storage overhead data goes to 0, which is kind of the interesting case when you're trying to minimize how much extra capacity you're using beyond you want to minimize the redundant portion of the data in the system. So that's beta going to 0. So it's R over C is equal to 1 over 2 beta is necessary. Greater or equal to 1 over 2 beta is necessary for data longevity. Longevity. That word is not going to. Thank you. And so this was a So this is really going to be the main focus is discussing a little bit about this lower bound. There is a corresponding upper bound, which we spent a lot of time at. We actually built this system up to a prototype of this system and actually had it working and everything. And essentially what it does is it matches the lower bound. So it says that this is also sufficient. And there's a couple of papers. The first one is not as tight. This is the real system we built, and this is more of a theoretic. And this is with this was joint work with a bunch of folks I was at, some of who I'm still working with. Tom Richardson, by the way, is an amazing coding guy. He's the guy who essentially wrote the LDPC codes for 5G that Qualcomm deploys. So here's kind of a visualization of the bounds. So if you kind of think of the storage overhead data as being on the x-axis, the upper bound is this dotted thing here. That's kind of what you can achieve. The lower bound is this all thing down here, the lower one, and the 1/2 data curve is the big black thing in the middle. Right? And if you kind of look at that in a relative sense, where you normalize these upper and lower bounds by the two beta factor, you can kind of see how they converge to 1 as beta goes to 0. Now, these upper and lower bounds probably can be improved. I would guess that actually the answer is they're actually 1. But there's only so much you can do when you're trying to prove these things. So, an overview of the lower bound has these different components too. So first of all, and I'm really not going to get into the proof details, so don't get too upset. I'm not going to get deep in math or anything. I'm just going to give intuition about what's going on. So a phase is a sequence of 2 beta n distinct node failures. Remember, beta n is the overhead in the system, the capacity overhead. It's twice that. And in this initial part, they're distinct node failures, so you never have the same node failing twice. And they're occurring at periodic intervals of time, so they're kind of equally spaced intervals where these things fail for every 20 minutes. A new node fails, whatever it is. So the first part, which is this kind of compression limit, says that for a random piece of data X, so that's a random data, truly random, uniform random, for every possible phase. So for every set of 2 beta n distinct node failures, if the repair reads less than the overhead number of bits beta times c from those that fail before they fail during the phase, then X is not recoverable at the end of the phase. And I'll get into the intuition about why this is true, but it's really pretty simple. Essentially, you can think of this failure process as kind of compressing X if this is violated, and X is not compressible, right? So it's kind of a very simple information. The hardest part of this whole proof is the core limits, especially the first, which says that for every possible setting for the data, if you look at a random phase, either you're going to read more than the lower bound number of bits from the nodes, or if you don't do that, you read less, then at least beta C bits are read from those that fail before they fail with high probability. And that's kind of the core of the whole proof. And then based on that, the second part is essentially taking combine it with this to get this, which says for a random data piece right now and a random data, either more than the lower bound number of bits are read, or else X is unrecoverable at the end of the phase. So either you read more than the lower bound, or you're not going to be able to cover the data. And then there's some more stuff you have to do to get the main theorem, which says now instead of this kind of random phase, which all the node failures are distinct and they for periodic intervals. Now it's just a random Poisson node failures. And how do you get to that? And it's essentially the same thing with the generalized to this more general case. Does that make sense? People still following? They are.
What's the difference?
Between this one and this one.
In that?
Yeah, so the difference between this one and this one is here. I'll say a little more about it later, but here phase is sort of restricted. And they have to sort of periodic. So what's more general down here is the duration of time between those areas phone calls. So that's a little more important part is that it's just random failures. And there's some technical details when you're trying to prove these lower bounds, you're starting these new phases all the time. Where you start to kind of on the actions of the pairs, you have to be very careful when you try to open here and doing things that you shouldn't be doing in terms of your analysis, essentially. But it's really it's not really that important. Let me just give you. Let's go back to some simple stuff here. So here's a data size D that has capacity of 6 nodes. So your data can fit nicely into 6 nodes and it fills them up completely, right? And your overhead in this case is 3 nodes overhead. You've got 9 nodes total. Your beta is 1/3. And now let's suppose a node failures, right? And then you read all the data off another node. And another node fails. And then you read all the data off 2 more nodes. And another node fails. And then you read all the data off another node. And then another node fails. Can you say anything about what the situation is at this point? Is this data still recoverable? Yeah. So you can at most have what was ever on this node, this node, this node. Yeah. So you don't have enough data to recover it. So intuition is that you can't recover it. So that's data is definitely not recoverable. So instead, let's back up a little bit. Let's suppose instead that these 2 were read. So now can you recover the data? Yeah, maybe. When you're trying to prove lower bound, kind of give the credit to the algorithm and say, well, yeah, let's say you can recover at this point, but we don't know. But we definitely, you can't say you can't. So here's the idea behind the compression intuition. So here's all the data nodes spread out over, and I've written the first 2 data ends. So the first data end that failed. So there's nodes total. And now that's the size of your real original data. It fills up everything except for beta n of the capacity, right? Now, I'm said the first 2 beta n are going to fail. So this part is not erased during that portion, right? So this is still around. So we have D minus beta C unerased portion available to data. Now let's suppose that when those fail over there, the amount you read before the failure was less than beta times. The amount you failed before read was greater than beta. Can you recover the data? The answer is no, because you have all this, you can take whatever you read from there. If you lost all of it, it's greater. So what you have left is not at least D, and it's definitely less than D. And so this is kind of saying, and you can formalize this, but intuition here is that that's recoverable proportion. You need to recover from whatever was erased plus together with whatever you read in the thing. And that's really all you got. So if it's less than D, it's impossible to cover X because that would be a compression. So here's the intuition behind the lower bound. If you don't understand anything else, this is very simple. Let's restrict the repair so that it has to read an equal amount data from each node between each failure and always read at the same rate, right? So it really has to do that. And so you have a first node that fails, right? You lose all the data on that. And then you read some amount from all the nodes. So this is the portion you're reading from each. So actually, there's a huge number of nodes over here that are also little n nodes. I'm only showing the 2 beta n that are failing. So you're reading from all the other ones as well, this amount, right? And then another node fails. And then you read that same amount from all the nodes, right? Including all the other ones. And this process continues. And so you see, as that continues, that you're kind of, if you read at a rate where by the end of these 2 beta n things, read all the data in the entire system, that's just at the point where the amount of unread stuff that failed before you read it is this data. That's kind of the intuition behind the lower bound. Yes, Russell.
This is why it's
Yeah. Yeah. Yes, exactly. The factor of 2 is because this is a triangle.
I mean, I guess n is big enough. Slight loss in the.
Well, in this particular case, you're not able to recover the data because this is slightly smaller. Right? So it'd have to be slightly higher rate to be able to recover the data.
Right, no, but the half is the height of the columns. Loss for.
Yes.
It'd be slow, it'd be a slow amount. All.
Yeah. So this is slightly less than half here. Right? And so because of that, you're not able to recover the original data. Slightly more than half, which means you read at a slightly higher rate, into slightly higher. Then you fill up the blue, it over that time. In which case, you could say that maybe you could recover the data. So again, this is a special case where you have this equal read repair. So this is just showing this triangle that we just talked about among the first data n. And of course, the blue fills in the rest as well, because you're reading from all the nodes. So the simple calculation, number of node failures in the phase is 2 beta n. So we set it to, so they erase the path back to that. If you read at an equal read rate of r slightly greater than, you kind of pull up this triangle blue that makes it slightly bigger than the red, then you can recover. But if you read at any rate below C, then the red is going to be bigger than blue, and you're going to lose much you can't recover. That makes sense? And so based on this, for this equal rate repair, there's it's easy to prove lower bound, which is exactly what we want. The read rate divided by the erasure rate. Okay. So let's just talk about the equal read restriction on repairs is pretty severe. Actual repairs in practice don't read, they often read unequal amounts from different nodes, right? And we want a lower bound on all repairs. So in fact, if you introduce an unrealistic model where the repair knows about all future node failures, right? Then for an equal read repair, this lower bound still applies to that unrealistic model, or even if you know about all node. But there's a simple very simple repair that beats that lower bound by a huge factor. What that simple repair does, since it knows about which node is going to fail next, it just copies all the data on the node that's just about to fail onto the node that just failed, right? And just sort of kind of preserves that. And it achieves a ratio of 1, even when beta is 1 over the lower bound. So the whole point of this is that a realistic model, you really have, the repairer doesn't know in advance what the failures are. The repairer doesn't know about that, and they just randomly fail. And then the other thing that's really important is the repairer can read arbitrary amounts from each node between failures. It's not restricted to having to read an equal amount from each node. And it can depend, that amount of reads can depend on all previous information that the repairer knows, including past node failures, past information read by the repairer, etc. So it can depend on everything. So how are we doing on time? Okay. So maybe I'm not going to go through this, but this is the hardest lemma in the paper to prove. I think this core lemma 1, which says that for every fixed setting for the data for a random phase, where again it's a series of distinct node failures that occur at regular intervals, periodic intervals, either more than the lower bound number of bits are read from the nodes or less than beta C bits are read from nodes that fail before they fail with high probability. And sort of the basic thing that makes it a little bit difficult is the repairer may read at a rate above or below the lower bound. You don't know what's going to do. So essentially, one thing you need to do is look at prefixes of amounts read by the repairer, the failures occur in a phase, and if it goes above, the average is above it, you just work the phase and start a new phase. And then there's all kinds of things that make it a little more tricky. So there's actually a reduction from the original repair to a second repair, where the second repair has this property, it never reads above the lower bound, but it gives a bound on the first repair about that event that happens. I think I'm not going to go into details about how that works. There's super martingales involved in lots of details, but a lot of fun to work on. But I'm certainly glad it's over. So here's sort of an intuition about that aborting thing. So here I'm sort of, these are node failures that are happening as time goes along here. Here is your lower bound. That's the B line here. And the height here is how much data you're read between these failures. So this much data here is here. And you see here the average that it's read is below the lower bound up here. But then after these two reads, it's above here. What you do with that case is abort it. Say, okay, the average is above the lower bound, start a new phase, do the algorithm. In this one here, it turns out, even though it goes above individual the prefix of how much read, it's always the average. And so that one goes to the end of the phase. And for this is the one where you prove that actually it didn't read enough data from nodes that failed before they fail, and therefore it won't be able to recover data. So this is the second lemma. I'm not going to go into details, but as I said, it's just a combination of the first lemma plus the compression. It's a pretty simple application. The main theorem, and this is what Russell was asking about before, so you have to go for show that most failures are distinct when failures are random. That's pretty straightforward. This is a little more tricky to stitch together many aborted phases because you don't know what the repair is doing. It might do something where they're really short and whatever. And somehow you still want to stitch all those together and where they start and end depend on each other. And so there's some complications in doing this part, but overall it's not that bad. And then the last part is pretty straightforward. periodic failures too, also timing failures. So this is really my last slide. So there's a lot of other practical issues in these systems. Transient node failures turns out to be a big problem. What happens in these systems is a node stops for a while, and maybe it comes back 10 or 15 or 20 minutes or 30 minutes or an hour later. Do you repair it or not, right? And that's a big problem, right? Because it's very expensive to repair these. They're not really broken. Often, you know, yeah. So go through this repair process to think it's permanently failed and it's not going to come back, in which case you better go and repair it. So there's kind of this race going on, right? It's permanently dead, but you wait a couple hours before you start repairing it. Doesn't do much for the integrity of your data because you might get behind, right, in terms of repairing it and so on. There's often, you know, unrealistic in some sense to say you immediately replace a node that's failed with a erased node that has the same capacity. Often you kind of come in batching. The node failure rate changes because some batches of service they put in have the failure probabilities in the previous batch, and this actually happens in practice where it can vary by a factor of 10 or more. Violent corruption is a big problem where it's corrupting bits, but you don't even know where they're happening. And so they do this scrubbing all the time to kind of read all the data from the system and figure out where the bad parts are and kind of repair those and so on. So that's a big issue. And then obviously the repair is not. So this floor bound, even though the repair is kind of shown as centralized, obviously all the results apply even though it's distributed around or whatever. There's nothing that affects that. In real system, the repair is obviously not just one process running, but there's a whole process running all over the place that are doing this repair in the distributed. All those are kind of practical. But in the sense of the theory, I think going from a model where bits are erased to bits are corrupted is really interesting. I'm not going to work on it. I love other people to kind of look at that and work on it. If you really think that this was sort of a strategy where these nodes are just not even kind of abstract. And all you're really looking at is how much data passes down there. But if you really think of that space or whatever, that could be pretty interesting. And I don't even know how to approach that. So that would be really interesting to have a theory of that. And all this is kind of interesting to me in general because my memory is really bad. And I have to kind of keep saying things so that I kind of reintegrate things in my own memory. So I kind of very much am fond of this kind of study.